So our next speaker is from Pulsar HRI, Miguel Lopez. Is it working? Yeah. Okay. Let's give him a hand.
Hello, everyone. Thank you for joining us. Today, I'm going to be talking about why hardware is not being solved. Sorry. It's just going to be a minute. Pulsar HRI is a spin-out from a research center in Tenerife, which is called Archimede Research Center. It's a publicly funded research center. We have been researching in robotics for the last 4 years, and it's just recently that we launched the company to sell our products. Our mission is basically to create the best-in-class actuation technology for highly dynamic robotics. We are trying to seek the absolute best performance in every single bit of the actuators, and we understand performance as a combination of capabilities provided by good electromagnetic design, mechanical design, power and control electronics, and control strategies. And we approach the design of this kind of technology through a model-based methodology. So we have a full digital twin of everything we do. The challenge when designing actuators is basically that you want to maximize the torque density and the accuracy and efficiency and the back drivability and the bandwidth, but most of the time those parameters are contradictory to each other, so whenever you try to optimize one, you basically are worsening some other parameters. There are just a few design philosophies when approaching the design of actuators. On one side, we have direct drive, which most of the time doesn't get the torque density required. And on the other side, the opposite side, is high gear ratio transmissions, which are the most common ones in robotics. And kind of in the middle is quasi-direct drive. So this is a very simple way to put things. We take a few evaluation parameters that I just mentioned before, and the graph very simplistically represents what each one of the design philosophies produces for the user of the actuation technology. And the key is always to try to achieve a higher torque density without worsening everything else. Apart from that, or on top of that, you have a lot of design variables for each one of the evaluation parameters. So these basically represent a huge design space, and it's really difficult to manage every single design decision. What are we doing to solve this, or trying to solve this? So the first design choice we made was to go for the quasi-direct drive solution or design philosophy. Not because it is the best, but because it's very versatile, and we think it's full of potential. We are working on 4 pillars, technologically speaking. The first one is basically to boosting the motor technology. We're trying to, and we're doing increasing the torque density and the efficiency at the same time of the motors. And we do this thanks to the multiphysics digital twin-based methodology that I just mentioned before. The second pillar of research or topic, it's about transmissions. We are developing our own transmissions, trying to lower the inertia to increase the bandwidth of the actuation technology. We are achieving a zero backlash from first principle with PGT-like efficiency. And then the third one is electronics. One of the most important things that we have done is basically to achieve high resolution, high frequency, integrated torque sensing with nearly 20 kilohertz of sampling rate. We're also working on commuting the motors at a higher frequency, which increases again the torque delivered and the efficiency, and also on achieving more than 10 kilohertz control loop frequency. And last but not least, we're also working on metrics and standards to characterize things like backdrag torque and backlash and bandwidth, both in speed and torque. Why do we need novel metrics? Because most of the time, the performance is evaluated on a single metric, and it is necessary to evaluate several performance metrics at the same time. And the constants, the motor constants are not enough. They are provided as a single number and not rigorously indicated how and in which conditions have been calculated. We are proposing new methods of testing that we have published and we will keep publishing. Particularly, the video I'm showing is a video of speed bandwidth testing that we just proposed on a paper for ICRA 25. Hopefully, some of you will review it and find it interesting. That's the sound of an actuator with a 100 hertz speed bandwidth. That's how it sounds. These novel metrics are allowing us to evaluate several performance parameters at once, quantify the effects produced by controlling electronics or decouple them, and rigorously quantify some of the parameters that I just mentioned before. In terms of scalability, there's also a challenge. It's very difficult to customize the solution and to do it fast and effectively. So that's why the first thing we did was to create a full multiphysics digital twin of our actuator, so we can basically simulate every single design parameter on the system. And thanks to this, basically thanks to the digital twin, we can design any motor in about 4 weeks from requirements to design for manufacturing. Several designs can run in parallel, and our error has been quantified in less than 2%, including linear and nonlinear phenomena. In the last 6 months, we have designed a whole motor and actuator range, thanks to this. And we are very proud of this. And if you're curious, we are in booth 10. So thank you so much.
Thanks very much, Miguel. So if you were wondering what was the loud thing in the exhibition hall.
My fault.
Yeah. Any questions from the audience? I see a hand over there. Just there, I think, 4th row. Yeah.
Thank you. Very nice talk. I was wondering, what is the sweet spot for the bandwidth that we need, both for the force sensing and then also the control bandwidth?
Okay, it's a good question. So far, we're trying to achieve as much as possible. I guess to answer your question, the first thing we need to do is to quantify it and then use it on platforms and understand what's the relationship between the agility and the performance of a platform depending on the bandwidth achieved by the actuators. That's kind of the next step for us, and that's why we put some effort into rigorously being able to characterize and compare different motors and actuators bandwidth. So I'm afraid I cannot answer your question right now. I might be able to do it in a few months. Sorry.
All right, thanks very much. Let's thank Miguel again.
Thanks.